Já estamos ao vivo, tá, Hélio? Pode dar início.
Okay, so welcome. We are here today to see Daniel Souza Correa presentation of his work for his doctoral degree. And we have, in the committee, we have Professor John Pali from Fermilab. We have Professor Laura Colucci from the Technological Institute of Aeronautics. We have Professor Vitor Paoloni from University of Pittsburgh, if I'm not wrong. We have Professor José Elayel from CBPF. We have Professor Giovanni Alves, also from CBPF. We have Professor Jorge Morfin from Fermilab. And am I missing someone?
No, I think that's all.
Okay, we also have Mrs. Larissa Silva from the CBPF Graduation Department. That's the secretary to this presentation. So the way things work is that Daniel is going to have 50 minutes for his presentation. Although the committee is free to ask a question, but you ask the committee to keep your questions and comments for after the presentation. Unless there is something very urgent, so please try to keep your comments and questions for after the presentation. So once Daniel is over with his presentation, we open a session for questions and comments from the committee. Okay, and after that, the committee will convene privately to discuss the work and come to a decision. We have just one observation. After about 1 hour presentation, Daniel will have to change room because the room is now at Fermilab is going to be used for another group. So this is not going to be a problem, just change the venue. Okay? Any question before we start the presentation? No. So Daniel, you have up to 50 minutes for your presentation. You may start when ready.
All right. Thank you, Professor Hélio, for the information. Good afternoon, everyone, and welcome to my doctoral defense. By the way, can you hear me well? Everybody can?
Yes.
So yeah, thank you for the members of this thesis committee for taking the time. And today I'm going to present my doctoral defense. It's about a measurement of charge current, mu neutrino, and antineutrino double differential cross sections on Minerva hydrocarbon target for the shallow inelastic scattering region. So I divided my presentation in 4 blocks. First, I'm going to introduce neutrinos in the Minerva experiment. Next, I'm going to present the region of interest of this analysis, which is the shallow inelastic scattering region. And after that, I'm going to discuss the cross-section measurement procedure. And finally, the results and conclusions. Okay, so neutrinos in the Minerva experiment. So the first question is, what are neutrinos? According to the standard model of particle physics, neutrinos are massless and chargeless leptons. They appear in 3 types of flavors: electron neutrino, mu neutrino, and tau neutrino. And they interact with the other particles within the standard model via the weak force, described by the Glashow-Salan-Weinberg model. However, several independent anomalies were observed from the late 1960s, and they built a compelling evidence that neutrinos undergo oscillation. I listed here some of these works. One of the most famous was presented at the Neutrino Conference in 1998. And here on this plot, you can see a deficit of mu neutrinos as compared to the prediction from the standard model. So if neutrinos oscillate, that means neutrinos have mass. And here is an illustration of this oscillation phenomenon. An electron neutrino can oscillate into a mu neutrino, that in turn can oscillate into a tau neutrino, and so on and so forth. So what we observe is the flavor eigenstate, electron neutrino, mu neutrino, and tau neutrino, as I mentioned before. But what actually oscillates is the mass eigenstate. And these two eigenstates, they are connected via the mixing matrix given through this equation. And we can take the two-flavor approximation to gain some intuition about this phenomenon. So the oscillation probability of a neutrino alpha going to a neutrino beta is proportional to an amplitude given in terms of an angle between these mass eigenstates. And it's also proportional to a frequency given in terms of this mass square difference between these eigenstates. And this oscillation phenomenon opened up a series of questions and is still unresolved to this day, more than 20 years later. And some of them are here listed here. So, for instance, side neutrinos, they own antiparticles. In other words, is there a CP charge parity symmetry violation in the weak sector? Another question is, which neutrino is the lightest? Do they follow the normal ordering scheme or the inverted ordering? And another question beyond the standard model physics is if there is a fourth neutrino out there. And I put some notes here regarding the recent measurements trying to address these questions. For instance, the joint analysis between NOVA and T2K published last year on Nature, the data show no strong preference for either mass ordering, but they note that if the inverted ordering were assumed, then the result would provide an evidence of CP symmetry violation in the lepton sector. And regarding the fourth neutrino, the Microboon collaboration also published at the end of last year these results, and they didn't find a sterile neutrino. So now the question is, how can cross-sections can contribute to answer these problems? So let me remind you what the oscillation experiment does. So we measure neutrino interactions in a near detector, referred to close to the source of the neutrino beam. And we also measure neutrino interactions in a far detector. And by comparing these two measurements, we extract the oscillation parameters. It turns out that the number of interactions depends on the neutrino cross-section. So it's essential to make cross-section measurements because it's something needed. And when we look at, for instance, the current oscillation experiments, when you look at the systematic error budget, for instance, NOVA, and considering, for instance, the delta CP parameter, we see that cross-sections figure as one of the leading sources of systematic uncertainties. And again, if you look at T2K systematic table, we see cross-sections also figuring as one of the dominant source of systematic uncertainties. So it's essential to make cross-section measurements to understand neutrino interactions with Lara and eventually reduce these systematic uncertainties for future oscillation analysis. Okay, now with this motivation, let's talk about how can we produce and detect a particle that is neutral, extremely light, and barely interacts. So at Minerva, we observe neutrinos coming from the NUMI beam. Neutrinos are produced in a series of steps, and I'm going to briefly describe them here. So first we accelerate protons at 120 GeV and strike them into a graphite target. This collision produces several particles, among them pions, which are focused using a set of horns into a decay pipe. And the interaction of these pions with the decay pipe material produce muons and neutrinos. Those muons, they are absorbed by these apparatus and these layers of rock, and finally we get neutrinos. So at the baseline, we put the Minerva detector, which I will describe the next slide, but we understand this neutrino flux according to these uncertainties. Neutrinos has this uncertainty at around 3%, antineutrinos around 5%. And here are the plots corresponding to the Minerva medium energy and the low energy. On the left, it's for neutrino, and on the right, it's for antineutrino. And these uncertainties, we achieved this degree, this level of uncertainties by applying some constraints using external data, hadron production data, and also previous Minerva measurements of electron-neutrino scattering and inverse muon decay. They are described here on these papers. Okay, so now that we have an idea of how these neutrinos are produced, let's talk about the Minerva detector. Minerva stands for Main Injector Experiment for Neutrino Nucleus Scattering. It's a neutrino cross-section experiment located at Fermilab. It collected data from 2009 to 2019. And the detector has 6 targets. Liquid helium, located here upstream the detector. Also water, carbon, lead, and iron, also here. And the detector also has a central part made of scintillators, also known as active track region. And this central part is surrounded by electromagnetic calorimeters and hadronic calorimeters. And 2 meters downstream is located the minus near detector, which we used as a muon spectrometer to measure the muon momentum and charge. The detector technology is these scintillator strips. At the center, we pass optical fibers that are connected to PMTs, and that's how we measure the neutrino interactions. And these scintillator strips, they form planes, and these planes, they are arranged in such a way that we can reconstruct the neutrino interaction through this 3D arrangement. And I should point out that this is important, especially important when doing analysis on the target region. But in this analysis, we are focused on the central part of the detector, which is the hydrocarbon target. The neutrino interactions are reconstructed via a calorimetry process. First, we identify a muon track, which is illustrated here as this long and straight line. And this muon track must be associated to the one we measure at the minus near detector, reconstructed either by range or curvature. And the remaining activity is assigned to the hadronic recoil system via this equation. So this equation here, alpha is an overall correction constant, Ci is a calorimetric constant, and Ei, it's a visible energy. So by measuring this muon track and the hadronic recoil system, we can reconstruct the neutrino interaction. Okay, so now let's turn into the main topic of my analysis, which is the shallow inelastic scattering region. And we are interested here in neutrino nucleus scattering at a field GeV. It goes from 1 up to 100 GeV. And depending on the neutrino, the energy of the incident neutrino, we classify the interactions according to these categories, and starting with quasi-elastic scattering that produces in the final state a lepton in the nucleon. And at increasing energy, neutrinos can excite the nucleon into a baryonic resonance. And this resonance, when they came back to the ground state, emits a pion. And at even higher energy, neutrinos can resolve the internal structure of the nucleon and produce several pions. Reality actually is more complex than this because our detectors are made of denser materials, and so we have to account for nuclear medium effects. So we have to care about things like the initial state of the nucleus and nucleon-nucleon correlations. We also have to think about what happens with particles before they exit the nucleus. So here on the right, it's an illustration of several processes known as final state interactions, which are interactions that happen after the primary interaction. And all these can lead to misreconstruction of the neutrino interaction. So then on this illustration here on the left, we see these scattering processes, and SIS is illustrated here. It's a transition region between the delta resonant pion production and the GIS regime. And to better define SIS, let's change this slide. So SIS then is the kinematic region predominantly made of higher baryonic resonances, non-resonant and multi-quark meson production, and it also includes a delta resonant background. So because we cannot separate this delta resonant background from these other processes, we better define SIS in terms of the full momentum transfer squared, Q squared, and we complement the definition by imposing some restrictions on the invariant mass of the hadronic system W. So then SIS is defined by Q squared greater than 0 GeV squared and W between 1.5 and 2 GeV. This lower limit is chosen to reduce the contamination of the delta resonance, and the upper limit is set to avoid GIS multi-quark events. The SIS region is illustrated here on this plot on the right, and we see the delta resonance peak and also some predictions from generators. And I should also point out that neutrinos induced meson production in this kinematic region was studied more than 40 years ago in the Argonne National Lab and the Brookhaven National Lab bubble chambers. And since then, we didn't have any measurements until recently when Minerva produced the first high statistics measurement in the literature led by Minerva collaborators at CBPF. And this was a huge effort of our collaboration, and I would like to highlight that. And what is the importance, the physics and importance of SIS? So the first point is that we can describe SIS in terms of quark-hadron duality hypothesis. It's an hypothesis established in the 1970s, and it states that the nucleon resonance structural functions, when averaged over the resonance bumps, represented here on this plot on the right, when we average these bumps, it coincides with the GIS scaling curve at high Q squared. And duality was observed in the charged lepton sector, but not for neutrinos, and not yet. And if it were observed, then quarks and hadrons could be described by a common framework. We could then extend the GIS formalism down to the resonance region. In the meantime, while duality is not reserved, we have to consider then non-perturbative QCD effects, and these are very well described on this paper, the New Stack white paper. So then what is the relevance of SIS? Historically, as I mentioned, efforts have been concentrated on the delta resonant pion production, and the transition region between resonant and GIS is poorly understood. Generators, they fit the SIS regime to match the data, so there is no first principle theory. And another point is interactions in this region contributes to a significant fraction of events in dune, as illustrated here on this plot. Okay, so now let's turn into the cross-section measurement procedure. The cross-section measurement procedure can be divided according to this workflow. I represented here, I made an illustration of how these distributions evolve with the time. So before is the distribution of events represented by this blue line, and the red line is what happens after we consider these stages. So starting with event selection, we define signal and background and design a set of cuts to select these signal events and reject as much background as possible. It turns out that these cuts cannot eliminate all backgrounds, and so we need a separate step to treat the background and remove them from the sample. This is the step 2. And after remove the background, the sample, the interactions, they are not assigned to the correct bin due to the detector resolution. And so they migrate between bins, and we address that by the unfolding procedure. And we also lose some events because of reconstruction imperfections and detector acceptancy. And so we address that with the efficiency correction step. And after that, we normalize the distributions to certain normalization factors to have detector independent measurement. So this process is summarized by this equation. We have the normalization factors here. U is the unfolding matrix, N is the selected events, and this one represents the background. We pick then a generator to simulate the cross-section and also the variables. So we used Gini to simulate the cross-sections, and the most important models for this analysis are the Rennes-Segal and Bodek-Young models. Rennes-Segal described the resonance region, resonant interactions, and Bodek-Young the GIS scattering. And on the top of Gini, we also apply some corrections to better describe the data based on previous measurements. So the QE events in the low chi-square region, they are suppressed by 25 to 30%. Nucleon-nucleon correlation, also known as two-pit-to-hole process, is enhanced in a specific regions of energy and moment transfer by 50%. And we also apply an ad hoc suppression to the delta resonant pion production in this Q-square region. And we also have this reduction by 43% of the non-resonant background. So all these modifications define what we call as Minerva tuning V2, and this is the central value of the simulation. And the variables of interest are the transverse and longitudinal components of the outgoing mu momentum defined by this equation. So we define mu angle with respect to the incident mu neutrino. And from that, we compute these components. And we also are interested on Bjorken X and Y variables defined by these equations. E hat represents the hadronic energy, and E nu is the neutrino energy. Another point is the components of the mu momentum. They are measured directly at the Minerva and Minus detectors, and so they are very well reconstructed quantities, whereas the Bjorken X and Y variables, they are model-dependent quantities, and so they are quite harder to reconstruct. So then we define the signal of this analysis by these conditions. The first condition is the SIS definition, and we also add these other conditions due to detector constraints. So for instance, this third condition, the mu energy between 2 and 20 GeV and the mu angle less than 20 degrees are imposed so that we can reconstruct muons with reasonable efficiency. And this is illustrated here. And I also should clarify something here. We use two versions of variables. One is the true variable and another is the recall variable. True refers to the theoretical model predictions coming from the simulation, the generator, and recall are quantities, the same variables, but including the detector and reconstruction effects. So it carries also the detector mirroring. So this is then the signal definition. And now let's talk about the background. In this analysis, background events are classified based on regions of simulated hadronic invariant mass. We have 4 categories of background given by these regions of W. And these limits define regions of W populated by specific processes. And they are illustrated here on this plot on the right. So the first background we label then as QE background because we have a predominance of QE events, and then resonant background and GIS background. And here is the signal region. So then given the signal and background definitions, we apply a set of reconstruction cuts to select the signal events and reject as much background as possible. And after applying these cuts, we get this distribution of events. So this green area represents the simulated signal, and these other components are the backgrounds. The black dots, they represent the data, the selected data. And we want to get rid of this background. We want to have a pure signal distribution. And I also put here the table with the components of this signal. So we see that GNI-GIS and Gini heavier resonance, they make the signal region. And as background, we have GIS events, that regions of W populated by GIS events and delta resonant. And the selection purity is 64% for neutrinos and 68% for antineutrinos. So as I said, we have to get rid of this background, and this is addressed in the next slide. So the idea here is to constrain this background through a sideband tuning technique. So for that, we measure certain correction factors or scaling factors using data in regions dominated by background but poor in signal. And these define the sidebands, which are illustrated here by these regions. So we don't touch the signal region, but instead we use data from regions around the signal to correct the background, and then after measure these scaling factors, we apply them back into the signal region. And the measured scaling factors are illustrated here on the right. So in blue, you see the GIS background. In red is the QE background, and orange or yellow is the resonant background. So now let's see the performance of these scaling factors by looking at the most important sideband of this analysis, which is sideband 2, GIS dominated. So if you look at the data to Monte Carlo ratio illustrated here on these plots, in red, it's before the background constraint, and black, it's after applying these scaling factors. We see that for the mean variables, they work really well, but for the Bjorken X and Y variables, they reduce the disagreement in the sideband region, but they are not as effective as in the mean variable case. So another alternative that we could apply would be the singular value decomposition and try to improve this tuning process. So after remove the background, the sample contains this number of events of mu neutrino and mu antineutrino. And at this point, we have isolated the sample, but some events in this distribution, they are assigned to wrong bins due to detector resolution. And we need to address them, and that's why we also consider the unfolding procedure. So as I mentioned, event counts, they are assigned to wrong bins due to finite detector resolution and imperfect reconstruction. And this is known as smearing effect. We can see this smearing effect by looking at this migration matrix. For instance, for the Bjorken X variable, this is a row normalized matrix. And for instance, we would expect this to be diagonal if the detector were perfect, but there is no perfect detector. And so, for instance, if you look at this second bin, 19% of events that should be assigned in the second bin, they migrated to the third bin. And 80% that should be also in the second bin, they are in the first bin. So we need to account for this smearing effect. And the way we do it at Minerva in this analysis is using the Agostini interactive unfolding procedure. And the idea here is to find an optimal regularization parameter. This is associated to bias variance trade-off minimization. And we want to redistribute these events in the right bins. We want to compute to infer the true distribution using this migration matrix. And this is computed through these equations. And the idea here is finding a regularization parameter K that is optimal, that minimize this bias to variance trade-off. And in practice, this parameter, this regularization parameter is found by performing a series of studies using modified versions of the simulation, because we want a model-independent choice for this parameter, and that's why we consider many versions of the simulation. And in practice, we compute chi-square distribution and determine this parameter as the point in this distribution where the median chi-square touch the number of degrees of freedom and remain stable after that. So for Bjork in X and Y and the components of mu momentum, I found that the number of iterations to correct for the smearing effect should be 4. And then I applied this to get the unfolded distributions. So the next effect present in this distribution is that we lose some events due to detector acceptancy, and we can estimate these by computing the efficiency and correcting the distribution for this. And we estimate the efficiency through this equation, and the overall mean efficiency of the SIS neutrino and antineutrino sample are 32% and 35% respectively. And the distribution are shown here, and we see that at low parallel mu momentum and high transverse mu momentum, we lose a lot of efficiency. So we have to correct for these missing events. And finally, the last point is normalizing the distribution by some normalization factors, the number of targets and the integrated flux. We divide the distribution by the number of targets to have detector independent measurement, and the division by the integral of the neutrino beam is to have model independent measurement. And the factors, the integrated flux are here for neutrino and this one for antineutrino. And these are the number of targets, and you should also consider this factor. So with that, we come now to the results. And first I'm showing here the results for the mu variables. On the left is the neutrino distribution. On the right, it's the antineutrino modes. And the measured data are represented by these black dots. And the simulation is in red. It's broken down according to these Gini interaction channels. And to make our lives easier, we can evaluate the performance of the simulation if you take the ratio, data Monte Carlo ratio, and evaluate from there. So this is the ratio, the data Monte Carlo ratio to Minerva to NV2. And overall, we see that the simulation is not able to describe the data across the full kinematic range. We see here the data being underpredicted, even more for high transverse mu momentum. This is for neutrino and antineutrino. And if you look at the region of transverse mu momentum less than 0.5 GeV, then we see that it seems like the simulation in the neutrino mode describe better the data than for antineutrino, and that is attributed to the non-resonant Bayesian suppression correction that we have in the central value, and this was observed also in the SIS publication I mentioned before. So now the results for Bjork and X and Y variables. Again, we see discrepancy. This simulation cannot describe the data across this kinematic range. These variables, they are quite challenging to interpret because they are derived variables, but we can do some checks. For instance, we can check the Gini GIS component, and we see that at increasing energy, the Gini GIS component increases, and the Gini heavier resonances decrease at high Q square. So as I mentioned, these are model-dependent quantities, and that's why we see these error bars, bigger error bars as compared to the muon case. And of course, when we are reporting a measurement, we need to consider the uncertainties. At Minerva, we compute systematic uncertainties according to the using the concept of universe. Each universe corresponds to 1 sigma variation of some cross-section parameter. And for instance, this is illustrated here. In solid line is the central value, and then we vary one parameter in the cross-section model, and this shifts up the distribution. And if we make another variation, it can also shifts down the distribution. And then we compute, we take the average of the difference between these shifts and consider that as a systematic uncertainty. And in this analysis, we have 5 categories of systematics: the final state interactions, the flux, the interaction model, muon reconstruction, and the particle response. And let's take a look at the systematics for the muon variables. So we see here that the muon reconstruction drives this systematic uncertainty, is represented by this red line, and increases with the transverse muon momentum, especially after PZ greater than 4 GeV. So on the left is a neutrino mode, on the right it's antineutrino mode. And let's take a look now at the systematics on the Bjorken X and Y variables. Again, we see muon reconstruction being the leading systematic uncertainties in some bins. For instance, these low Y bins is we see the particle response peaking here in these low Y bins. And we also have the flux and the interaction model. And the particle response error source represented here by this in magenta for the particle response, the error source associated to this is the calorimetric response to pions. And this makes sense because we have at least one pion in the final state in this SIS region. And this brings us to the end of my presentation. And let me summarize. The main takeaways are, these are the first charge current double differential cross-sections for muon neutrinos and antineutrinos interacting in a hydrocarbon target in the SIS region. We observed poor agreement between these measured data and the Renyi-Segal and Bodekian models as implemented in Gini. These measurements contribute to fill a long-standing gap in the literature about neutrino-induced pion production in the SIS region since 1970s and 1980s at the ANL and BNL bubble chambers. And this data will serve as a benchmark for model improvements and control of systematic uncertainties in oscillation experiments. And these are the next steps. I have been working on this recently, implement a new flux constraint. And as we saw, the simulation cannot describe the data, so we are looking at new tunings. For instance, this resonance model due to gradient subject, and also modified non-resonant pion production. And it would be interesting to investigate neutrino interactions in the SIS multiquark region. This region is defined by Q squared greater than 1 GeV squared, and this provides reduced resonant background. And another topic that would be interesting to study is the nuclear medium effects in the SIS region through cross-section measurement on other Minerva targets. We could explore interactions on carbon, iron, and lead. And finally, I'd like to thank the Minerva collaboration, all collaborators who made this data available. And I'd like also to thank CAPS for the doctoral fellowship and also Fermilab for the support. And that's all I have. I'm done. You can also, question me.
Okay,
Thank you.
thank you very much. So now I go to the questions and comments from the committee. Usually start for those who are far away as possible, but this doesn't make much sense when you have the internet. So I'm trying to do some geographical things. So let's start with Jorge Morfin. Jorge, please, your comments and questions.
Yes, I do have a few. First of all, it was a very good presentation. I appreciated the effort that went into making this presentation, summarizing several years of work into a 50-minute presentation. It's not always easy. So my questions are twofold. One, can we go back to your slide 13? I think it is. Okay. So what I want to point out here is, and you know this is very well, we've gone over this before, is that the shallow inelastic scattering region is defined by Q squared, not by W. For Q squared greater than 0, there is still a lot of resonance production in your sample. To really get into the what's called the multi-quark SIS region, you need Q squared greater than 1. And what that means with Q squared greater than 1, you actually have interactions within the nucleon. So I just want to emphasize this for the people on the committee, that for Q squared greater than 1, we're in the multi-quark region, you don't have many interactions down by, you don't have many SIS interactions down around the delta. They're always at a higher W.
Yes.
But since you're defining Q squared, defining an SIS with Q squared, this is the way to look at it.
Yes, I have a plot for her in the backup slide, and I can show here. So this is the SIS region in green, the subject of my analysis. And what you mean is applying this Q squared cut greater than 1 reduces this resonant contribution to the sample.
Exactly.
So we're left with this portion of the region.
Right.
Right.
And the emphasis then is that with Q squared greater than 1, you're actually able to have interactions within the nucleon. The first nucleon within the nucleon interactions, because it's just above Q squared greater than 1, you get events in the non-perturbative QCD region, which means you're interacting with more than one quark, which is why we call it the multi-quark region. Okay, thank you. That helps clarify it.
All right.
The only other thing I want to raise, because I don't want to take up too much time with this, is if we can now go to slide 27. I want to clarify one thing.
Okay.
Okay. You point out here the low PT region between the neutrino and anti-neutrino. And you're saying that's due to the non non-resonant pion subtraction, right?
Yes.
In reality, I think it is much more the fact that we discovered for q squared less than 0.7. And remember, there's a nice relationship between PT and q squared. For q squared less than 0.7, there's a suppression of pion production that we've seen in Minerva, and they also saw in Minos.
Yes.
We actually made that part of the fit that we're talking about.
Mhm.
And it was made with neutrinos and just taken over to antineutrinos. And I think that's what's causing the difference. More than the non-resonant pion subtraction, it's the low q squared resonance subtraction that we found in Minerva.
Yes, I have those two components in my central value, as you mentioned. This is what you're talking about. This low
Exactly.
suppression.
Exactly. That's it.
Yeah.
That's the one that I think is causing the difference between neutrinos and antineutrinos in low PT.
Mm-hmm.
Okay. Other than that, it was an excellent presentation. Thank you.
All right. Thank you, Jorge.
Okay, thank you, Jorge. So Jonathan Polly, Professor Polly, and your comments and the questions?
Yeah, so first of all, fantastic presentation. Thank you so much. And yeah, this is really great work. I only have a couple questions. So probably no surprise to you who know me. Can we go to slide 8?
Okay.
So okay, so you claim an uncertainty on the flux prediction of, roughly 3 or 4%. That is, as I understand it, is that on the normalization only?
I believe so, John.
So that's like on the, I guess on the,
Okay. No. Let me check here. I have my. Can I show my thesis? I have the systematic uncertainties on the flux. So these are the uncertainties. Neutrino mode, antineutrino mode. So yeah, this also takes care of the shape between 2 and 20 GeV.
Yeah, so I didn't quite understand this plot. What is this is a fractional uncertainty. So how many universes did you use in the end?
Yeah, in the end I used 500 universes.
500, the blue, and the
the 500 is behind the green one.
Under the green. Okay. Okay, so I was going to ask, okay, yeah, I should have stared at that plot. What is the level? So this is the uncertainty as a function of energy. I'm trying to understand what the level of the shape uncertainties are, right? You have a rather broad band beam. I'm not sure I care too much about the uncertainties above 8 GeV or so. You have not much flux out there, I believe. But what is, I mean, I'm just wondering, because you're looking at kind of in a somewhat of an exclusive final state. And so there is an energy dependence here. And I just wonder, how are you, I guess, how are you accounting for the shape uncertainties in the flux?
This is a great question. I think I have to think about it. But I would say that we are also working on implement new flux constraints, as I mentioned at the end of my thesis, and I can show in the recent version of my thesis. It's not included in the one I sent you. I sent to the committee. It's some work in progress, but we are also planning to implement this low new method and constrain the flux using this parametrization for this energy range. So this also will be applied on the top of the current flux constraint we have. And we saw actually some improvement in the data, and we are planning to report this in a publication later. But yeah, for now, that's all I have to say.
Okay.
Mhm.
Okay, all right, thanks. And then with regard to your data-driven background constraints, right, using the sideband samples, it wasn't exactly clear to me. So when you use sidebands, one of the things you have to worry about is whether or not the backgrounds that are in the sidebands are kinematically, that they cover kind of the kinematics of the backgrounds in your signal region. And so is there a plot that shows that you cover the relevant lepton and hadronic, like kinematic, state kinematics in your sidebands, that they, scaling from one sideband into the signal region, like how valid is that?
Okay, so I have the backup of my thesis, the sideband definitions, and maybe that can help. Let me see here. General constraint, sideband definition. So we define the sidebands according to these limits on W. And so this is the based on a study of efficiency and purity, we define this, but I'm not sure if I'm answering your question.
Well, so there's a prediction of what the kinematics of the backgrounds in the signal region looks like. And then there's a prediction of what those, whatever background are that you have in your sideband samples. Have you compared the, I don't know, the like the muon kinematics and the let's say the W spectra of the sideband region versus what you expect, to have to cover in the signal region? Like, do you have full coverage of the full phase space of the bands?
I didn't do that study. So that means check if I have something in the backup regarding this. Yeah, sorry, John, I don't have this study here. Actually, I didn't do this study, so.
Okay. All right. And then there's also, I mean, kind of a corollary of this is that, there will be correlations between the events in the sideband region and the events in the signal region. And do you account for those correlations when you do your fit?
Oh, okay. So during the fit, we give as input the data from all sidebands. We perform a global fit, including data from all sidebands at once, and we fit beam by beam.
Right, I'm sorry, I misspoke. What I meant was there are correlations of across the bins in all of your sideband regions, right? There will be correlations. So when you do this all at once fit, do you account for the correlations, the bin-to-bin correlations
Yes, we do
in
that.
that fit, or are you kind of so you have a covariance matrix that you use in your chi-square calculation for the fit?
Oh, I see. No, we don't have a covariance matrix there. Yeah, we just give as input the backgrounds
Mhm.
and minimize this chi-square, like just looking at the number of events, like not looking at the errors. So
Okay. But presumably you know, when you do your systematic assessment, you're varying things. So
mhm,
at least you'll see what kind of sensitivity you do have to those
mhm,
correlations, so that
yeah.
should be fine. Okay. Okay, I think that's all I had. Thank you.
Mhm. Yeah, thank you, John. Actually, maybe I could say something about these correlations. When we compute this chi-square to see the performance of these models, to test the models against this data, then we use the covariance matrix to get these chi-squares.
Right, so you calculate a covariance matrix for the final measurement.
Yeah,
Yeah.
that's right.
Yeah, that's pretty standard practice. So good.
Yeah, right.
Okay.
Thank you, John. It's good to have you here in this thesis committee.
Okay. All right. Great job. Thanks.
Mm. Thank you.
Professor Paoloni, do you have a comment and question?
I'm sorry, Professor. Just a second. I think I should switch the room now because it's already 1 p.m. for me. So before Professor Paolon, can I just switch the room?
Yeah, of course. Yeah, I have several questions, so it's probably a good idea to do it now.
Okay.
Yeah. All right.
But it should take just 1 minute. So.
That's okay. Okay.
Okay, I'm going to disconnect here now.
I think this interruption might have been my fault. I think I had promised Danielle that I would reserve a room at Fermilab, and I just completely forgot. So I apologize.
Where are you, Victoria?
Excuse me?
Where are you right now?
Who are you talking to?
Yeah. Who are you talking to, John or me? I'm sorry. That's
Oh, well.
yeah. Okay. Oh, I didn't know he was at Fermilab. Okay, so he's at Fermilab, and he's running around. Yeah, the classic running from one room to another at Fermilab. Okay.
Yeah, I really want to turn that into a game.
Yeah, it's exactly. It's like musical chairs or some musical
Yeah.
rooms.
Musical rooms, yeah. Maybe at collaboration meetings, we should have like a bingo card when you check off which room you've gone to.
Yeah, exactly. And then we can have, yeah, that's right. Then you can have a prize for who gets
Who
bingo.
gets the most? Yeah. Or who fills it out first?
Yes, exactly. So here we go. I can ask physics questions on some of its initial slides, right? Is that
Yes, you can ask whatever you want.
okay? All right.
I'm back. Can you hear me?
Yes, I can hear you and I can see you.
All right.
So first, now, really nice talk. It was really well presented. I just have some questions about specific slides. So can you go to slide 5?
Yes. Okay.
Okay, so you say here, the things that we don't know about, neutrinos. You didn't mention absolute mass.
Yes, that's right.
Why?
We don't, in these neutrino oscillation experiments, we don't measure the mass, but the mass squared difference between these eigenstates.
Okay, very
So
good.
I have in the backup just to show you here what problems are addressed by each
Okay,
experiment. Let me just open here.
okay.
So yeah, so this question about, for instance, are neutrinos Dirac or Majorana, then we need to measure precisely the mass, but not the square of the mass, and this can be addressed by, for instance, double beta decay experiments, and these other questions are also can be addressed here by this range of experiments. So the one we are interested are these ones like what's the neutrino mass ordering addressed by accelerator experiment, DCP violation, so and so on. So
Okay, yeah, you obviously know. Okay, that's good. So then the other, I think on that slide, you said something. I mean, I'm on microboon, so you said something about that it eliminates the fourth neutrino. Is that completely true?
yeah, actually, what this publication set, it's like a sensitivity. So you are part of microboom, so then you know that this publication set actually an area where you like you cannot find this stereo neutrino with certain confidence level.
But it assumed a specific model, and so what was that? Do you know what model that was?
Oh, I'm sorry, I don't have that information.
Yeah, so it was assuming 3+1. That's the model that it used, and that's what it gave limits on. So
Okay.
it's not so it's a bit overreach to say that it eliminated this a fourth a stereoneutrino. It's eliminated a specific, it can put limits on a specific model. Okay, that's
Yeah. Fair enough.
okay. So
Neutrinos never die.
can you go to the next slide?
Yes.
So you say here, which is true, that the biggest systematic error in oscillation experiments is cross sections. But can you elaborate as to how the cross sections, why it's such a big effect? I mean, what is it doing that's screwing up extracting the oscillation parameters?
Oh, so as we saw here, the number of events that we count in these near and far detectors, they depend on these cross-section models. So these are propagated into the extraction of these parameters, but I don't know to a certain degree, like what actually is driving this dominant uncertainty. So
Okay, so look, so you see these equations, they have the variable that's in all of them is the energy of the neutrino. So how can the cross, so what will that, not knowing the cross section, will that have an effect on how you reconstruct the energy of the neutrino?
yeah, right. So one of the challenges is the reconstruction of this energy, right? Because you need to observe this final state, and from there we reconstruct the neutrino energy. So one of the challenges are the final state interactions,
Yes.
which can lead into this mirror construction. And yeah, this is associated to the hadronic recoil system. And the uncertainty arises from there. So this is my
Yeah, I mean, so look, I mean, what goes into the oscillation equation is the neutrino energy, and what you get out of the detector is some model for what the actual neutrino energy is. If you understand that map, you can correct for it, but if you can't, you will screw up the energy of the neutrino, and then you will shift all of the oscillation parameters, and that's where the error is coming from.
Oh, okay. I see.
Okay.
I see.
So understanding how to map from what you see in a detector to the neutrino energy is incredibly important when you're doing the oscillation experiment.
Mhm. I see.
Okay. Let's see. So John already asked a question about the flux, so I don't have to ask that one's exact question I was going to ask. Can you go to slides 13 and 14?
Yes.
Okay, so this is also a question I had when I was looking at your thesis. You have W, and so it's kind of related to what Jorge was speaking about, and I didn't realize that it's actually the Q squared that really defines it. But you do have W true and W reco, but I never saw it written explicitly how you calculate W from the.
W.
So, maybe because it's under one of my. So that's your formula you use to calculate the reconstructed W.
Yes.
Do you know what the resolution is on W?
I don't know on W, but I know on the hadronic energy,
Okay.
which is associated to W, and I have that on the backup. Let me just jump there.
Oh, you do have. Okay.
Yeah.
Was that in your thesis? I couldn't find it, but maybe.
Yeah, sorry, I didn't include these plots on my thesis. It was a
Okay.
written study.
I
But
see. Okay, good. Thank you. All right.
so
So it's
these are
about
the
20% or something. Or yeah, 15, 20%. Okay.
mhm.
And it's relatively symmetric, which I'm actually didn't expect. Okay. Can you go to slide 17?
Vittorio,
Yes. All right. Sorry.
yeah,
Go
I
ahead.
think I can add a little bit to this discussion on the resolution of W because we've been concentrating on that in the publication of the one-dimensional analysis of SIS. Could you go back to your formula for W, please?
14.
There we are. Yeah, no, that's it. First of all, this is assuming that the nucleon is at rest.
Okay. Right.
Okay.
Yeah.
And in reality, we are in a nuclear environment so that the nucleon is moving with Fermi motion and it's off the mass shell. So there are two W resolutions to discuss. Let me be quick about this. The resolution of W at rest versus the resolution of the W, which includes the nucleon moving with
Right.
Fermi motion, is on the order of 9%. So there's a 9% contribution to the resolution of W just coming from the assumption that the nucleon is at rest.
Okay.
Then if we take the measurement of W, it includes the measurement of EHAD,
Mhm.
of the nucleon momentum, and the nucleon, the muon momentum and the muon angle. Of these three, we find out that the hadronic energy contributes 16% to the resolution of W, whereas the angle and momentum of the muon contribute like 1%. So it's the hadronic energy resolution and the assumption that the nucleon is at rest that's contributing mainly to the resolution of W.
Okay. All right. But it is around 20% then or something, right? Is that what
Yeah, it's close to that.
Okay.
It's closer to 18, but 18,
Yeah, all right. No, I
no
couldn't.
difference.
I couldn't do the fit that accurately. Sorry on the fly. Okay. Okay, thank you. Okay, can you? I'm sorry for all the questions here. I'm curious. So that's why.
Yeah,
So can you go to slide 17? Because this is really nice work.
17.
Yeah, so this actually may be a question to both you and Jorge. So are you telling me that there is no model in Genie for SIS?
No, there is no model there for
There's
S.
no model, so it's new
We use-
exploration. Okay.
Yeah, we use a mixture of
Yeah. I mean, these are spread into each other, into
Yeah.
that region that you call SIS. And so you're just, you're in virgin territory, in other words.
yes.
Okay.
Can I make a comment? Just
Yes,
short.
go ahead, Jorge.
I promise to keep it short.
Okay.
The thing is that with SIS being defined by Q squared, not W, but by Q squared,
Yeah.
you can have SIS events across the W spectrum.
Mhm.
Okay. The SIS physics is dominated by non-perturbative QCD, and non-perturbative QCD is part of the Bodek and Yang what's called DIS model.
Okay.
This DIS is not what we call kinematic DIS, but it's the Genie DIS, the Bodek-Yang DIS. And they have attempted to incorporate both higher twist and
Mhm.
target mass corrections into their definition of a new Q squared dependent variable that they use in extrapolating down into the SIS Q squared region. So there is a model. There is a
Okay.
model that comes out. It's a model that's unfortunately based on electroproduction
Mm,
results. So you have to be careful about what the axial vector contributes.
right.
They've made estimates, and that's the best model we have.
Okay. So it's a good thing we're measuring this because
Exactly.
Yeah.
Exactly.
Okay. Very good. Okay. All right. Let's see. I'm getting close to the end here. So 23, slide 23. Oh, so let me just make sure I understand. So you have this plot on the right, and then you have these equations on the left. Can you tell me what the plot on the right, what variable in your equations it's representing?
Yeah, sure. So this plot is showing the migration matrix. It's
So it's M. Okay. So it's
yeah,
M. Okay.
it's M.
All right. That's
Yeah.
what I thought. I just wanted to make sure.
Yeah, we start with a prior,
Right.
and then we compute this unfolding matrix from the elements of the migration matrix, and we keep that updating at every iteration, and that's how we get the unfolding matrix, and we use that to infer the true distribution in the correct bins. So,
Okay.
mhm.
Thank you. But thanks for the clarif. So in your thesis, you should be clear that that's M, and you're calculating U from this plot. Okay, because it wasn't clear in your thesis that
Oh, okay.
that those the connection between the equation and the plot.
Okay.
Okay, so let's see. So slide 27. So this is basically your result. So this is something maybe I missed it, but in the thesis. So the protons on target that you collected and used in this analysis are both forward Horn current data and reverse Horn current data, right?
Right.
But it's not listed anywhere as to what
Yeah.
the specific number of POTs were taken with forward Horn current and what was reverse Horn current.
Oh, yeah. So this one, I think it's there is a typo here, but this one is for the neutrino. It's very tiny. Don't know if
Yeah,
you
I couldn't.
see.
Okay.
And this one was supposed to be for antineutrino, but I think there is a typo here. So I
Okay.
have to double check that.
Yeah, so in your thesis, you should be clear when you talk about when you collect the data, what was antineutrino and which was neutrino. Okay, because I couldn't find, maybe it was in there and I just didn't see it, but it wasn't that clear. It should be, because this is a document that's can be used by people in the future, and it's good to have all of the details listed in your thesis.
Yeah, sure.
Okay. And my final question is slide 31 and 30. Just go to 31. It's just a question about, you mentioned So the major systematic error is muon reconstruction. Can you elaborate what you mean by muon reconstruction? What aspect of muon reconstruction was the problem?
Yeah, so I put on my thesis, I think on the appendix, the breakdown for each of these group, and we saw that the Minerva component of this group was the cause of this uncertainty. So we measured muons at Minerva and minus near detector by looking at the energy deposition, and we have some error source associated to the mu momentum and the angle, and from there we assign some uncertainties on this reconstruction. So the the one driving this mu reconstruction is, if I'm not mistaken, maybe I can look at my thesis and tell you exactly what you one was, but I believe it was the Minerva energy reconstruction.
Oh, so it's not the
The
it's
Minos.
not Minos, it's not Minos that
Yeah. Surprisingly, it's the Minerva
I see.
one.
Damn, I thought I could blame Minos. Okay. So, okay.
Yeah.
So it's okay. So it is Minerva. All right. Okay.
Mhm.
All right. Very good. That was all my sets of questions. I'm sorry for the long list, but a really nice
Oh,
talk. It was
no.
really, really nice to listen to.
Yeah, thank you so much for your questions, and I really appreciate you for being here. Really nice to have you.
Thank you, Vittorio. Now, Professor Colucci, please, your questions and comments.
Okay, hi. Well, first, thank you for the invitation. It was very interesting to read your work, and it's clear that it's a very well-developed work. And your thesis was well written, which is not so often to see nowadays. So congratulations on that. I just think that at some parts, I know that it's a very large work, so the thesis is already very large, and sometimes it's very hard to get into many details, but some details, for example, what was just mentioned about the muon reconstruction problems, since it directly impacts your results, I think it could be better described. In particular, I found it, I would find it interesting to have more details on the simulation and reconstruction of NERPA. And in particular, sometimes you put some references like this is done because of this reference. And like I said, if it directly impacts your results, maybe it would be a good idea to explain a little better. And I have to say there is a DocDB reference, which is not publicly available. So this is something you should avoid.
Okay, yeah, sounds good.
Yeah, since I'm not a Minerva collaborator, I could not see anything related to that. But in any case, could you elaborate a little bit on the how your results, this was made for a region that is not very well explored, I understand. But can you tell me if how your results compares perhaps with other results from other experiments for the same region, or even results that you have for cross sections in Minerva in other regions? Do you usually find the same kind of problems in other analysis for cross sections in Minerva?
Yeah, usually we see this discrepancy between this measured data and the simulation. This is a systematic problem across many analyses, but I don't remember now one specific case which I could point out. But to see. Yeah, I made these model comparisons for using other generators. For instance, this Newt, it's used in T2K. I also compare against a new row, and all of them are wrong, one better than the others, but new row seems to be the best one, but all of them has some degree of imperfection, and but against all the data in other regions, no, I don't have this information, because yeah, you might know as well that these results are the first after 40 years of this gap, and it's we published last year our first result in one dimension, and it was the first after this long time. So, but yeah, I think I don't have a straight answer to your question. Sorry. But,
So, no problem. This was more to try to understand the broader view of the problems that you have. Maybe since there has been a lot of questions already in this part, I could try to discuss a little bit one thing that is in your appendix.
Mhm.
I think it's the last appendix that you included about the work that you have made with argon purification.
Oh yeah, sure. Yeah, that was my harder work. I didn't talk about that in my presentation, but yeah, we can discuss that. I'll be happy. Maybe I can share my screen here. This is a work important for Dune. This development of a liquid argon filtering to remove nitrogen from liquid argon, and that impacts the reconstruction of the neutrino interaction graphics. So it was a work I performed in Brazil at the Unicamp, and we also did some experiments here at the Fermilab, and it was
It's a little bit too soft here. Can you increase your volume?
yeah, maybe I can.
Good.
Yeah, can you hear me now better?
Speak closer, please, to the microphone.
Yeah, sure. So yeah, Professor Laura, yeah, you can ask a question. Sorry, you can go ahead. Mhm.
Sure. Okay, so you have described the work that has been done, but it wasn't very clear to me exactly what was your part on the whole
Oh,
work. I mean, did you help
Mhm.
with the measurements, with the analysis? What exactly did you do?
Oh, okay, sure. What I did was the data taking. I contribute to acquire the data, perform the experiment at Unicamp, and I also contribute to the data analysis. We measure this signal from PMT, and then we like assessed the argon impurity by extracting the decay time associated to the nitrogen contamination, and I extracted these lines here showing how the purification in liquid argon evolves as we use this filter to remove the nitrogen. So yeah, I contribute both to data analysis and to the data acquisition. And this led us to a paper I think I listed at the beginning. So yeah, it was because Minerva, when I joined the collaboration, everything was done. So we had the data available, and I did this data analysis. And my supervisor, he told me that it should be good also have some hardware experience, and that's why we also contribute to this effort for Brazil. So yeah, these were my contributions.
Interesting. Is this something you plan on keep working on? I mean, what are your plans now that you are finishing your PhD?
Oh yeah, so this hard work was performed in 2023, and it was like I think a 9-month experience. So at some point I stopped um, working on this, and I focused only on my data analysis. So the next steps, we are planning to uh, report these cross-section results in a publication. So there is some work to be done. I have to, as I mentioned here, I have to extract cross-sections for this SIS multi-quark region defined by this. And so my plan is finish this work, the data analysis, and report this. But that work from the hardware part, I'm done with that.
So your idea is to perhaps get a postdoc at Fermilab and stay there keep working on Minerva.
Oh yes, I will be working on Dune and on Minerva at the same time. Actually, I joined. I'm also part of Dune, and I will be doing a postdoc on Dune. Another front, but I still have this to finish. Yeah, John knows about this, and yeah, I'll be working on Dune, and because Dune is the future, so. But yeah, I have to to finish this analysis.
Okay. So yes, I think I'm happy with my questions. Just again, congratulations for the thesis, and I would just like to have seen a little bit more of the simulation reconstruction details, since I'm not very familiar with the detector. But
Oh, okay.
thank you for your answers.
Yeah, sure. Thank you, Professor Laura. It's good to have you here, and I'm going to provide more details on the reconstruction part. I know that this experimental part of Minerva, I was not too extensive in the description, but yeah, I can do that. Thank you very much for your comments.
Okay, thank you, Professor Alucci. Professor Eliel, please ask your question and comments.
Okay. Okay, so Elio and Daniel, thank you so much for the invitation. It was very good to read the thesis and to see how Daniel developed since 2022, when we first met, when you came to do your PhD at CDPF. We discussed the several issues because you were following my course on fundamental interactions, especially the electroweak theory. And I was very surprised because you have had a very theoretical training, and you were moving to experimental physics, experimental particle physics, which is not an easy transition when you are at PhD, because from strong backgrounds on theoretical physics, now to move during the PhD for a high energy experimental physics is not an easy task, but you did it very well. I am very glad for the quality of your text. I am an outsider theorist, but I can tell you that I could read your thesis, without problems. Everything is very clearly stated. I know where I was, even though I was not understanding everything, all the technicalities involved in your work. Your presentation was also very good, very clear. I mean, you did it in a very good rhythm, showing that you are really knowing about what you have done. And I hope, you succeeded to have good postdocs, to go ahead in your career. Now, I have some questions. I mean, understanding that I'm a theorist and I am very interested in your work, but always thinking about possible physics beyond the standard model, looking at the looking from the neutrino sector. No, so my first question, it's a very naive question, but what is I mean, if you move from the mu neutrino to the tau neutrino, what is the difference? I mean, technically, experimental wise, is much more difficult, or what? I mean, are there people or groups also trying to see the tau neutrino, anti-tau neutrino interactions? What are the main difficulties? I mean, just tell that for a theoretician, please.
Yeah, so from my understanding, produce these tau neutrinos, it's at some extent hard. Yeah, but exactly why it's hard to produce, I'm not sure. What I know is we have these mu neutrinos in this sample, and also some contamination from electron neutrino. But the tau neutrinos, I'm not sure. But I know that if I'm not mistaken, Professor Paolon was also involved in the discovery of the tau neutrino.
Very good. So I'm drinking water from the source. So, sir, give some hints, please.
Okay, so the issue is, first of all, it's a kinematic. There's also a kinematic limit, threshold, which the beams are at 6 GeV. So you're right at the edge of where you can. I think it's 3 or 4 GeV you need for the fixed target current. So you're close to threshold. The other thing is, how do you identify that it was a tau neutrino interaction? You have to see the tau, and the tau is a picosecond, and so you don't see the attached vertex, and most of the decay of taus are into electromagnetic kind of like pi zeros and rhos.
I see.
So what you'll see, what you need to look at is you can do it kinematically, but you have to see an excess of like electromagnetic kind of final states, and it would be based on the higher energy tail of the neutrino, but it's a rate problem also. It's just it's a very it's a very difficult neutrino to see, actually. Okay, there's only there's only like 20 compared between Opera and Donut actually seen individual events. I mean, but because basically it's because the tau is such a short-lived particle, and you have to have a lot of energy in the incoming neutrino.
I was wondering something like that about the tau. No, okay, thank you, sir. Thank you so much.
You're welcome.
So back to Daniel. So Daniel, also from your studies, which sort of physics beyond the standard model can you try to detect, even a very tiny effect from your experiment? Is it possible to get some, for example, CPT violation? We know, I mean, theoreticians work a lot nowadays about Lorentz symmetry violating possibilities beyond the standard mode, CPT violation, and also many other paths like supersymmetry, extra dimensions, but I'm not talking about that. I'm just talking about CPT violation. Is it possible to get any possible signal of CPT violation from your studies?
Well, Professor Elael, in my analysis, I didn't look at any of these new physics and break of these symmetries, but maybe I should make some propaganda here because we released the data. All Minerva data has been released last year. So we provide everything and also tools to analyze the data. The tools I used in my analysis, it's all now public. Everyone now can use. And maybe if you are interested in looking at this new physics and do these
Yeah.
studies, or if you have a student interested in maybe check the theories you are
Yeah.
building against this data, it's now possible. So everything is
Okay.
available here, and you can do now.
I can get that from Minerva, no?
Yeah, you can get on
Okay,
this
very good.
address,
Aha,
and
very good.
everything is there, the tools, the data,
Mhm.
and
Okay.
yeah.
Because in our group we have 2 students working on possible signals of new physics, no? But
Mhm,
I would like to enter the neutrino sector that we have not yet contemplated. So,
mhm,
okay, good information. Okay, Daniel, I'll be in touch with you, okay?
mhm. Yeah,
Sometimes
sure.
I will write back to you just to get some, let us say, information,
Mhm.
reference, or even your opinion, okay? Thank you
Yeah,
so much.
I
And just finally, I mean, what happens? I mean, let me put this way. Uh,
mhm,
does your experiment fail if neutrino comes out to be Majorana?
mhm. Uh, what would happen if
Yes.
neutrinos would be Majorana? Oh, this is a good question. Uh,
Maybe it's too long answer. You can think about, but I mean,
yeah.
look, I mean, sometimes we are innocent and we ask
Uh-huh.
very difficult questions without knowing that they are difficult. And I don't want to take you very far from your path. But I mean,
Uh-huh.
it was just a curiosity that I have that if you have Majorana neutrinos now, I mean, does this experiment make sense to study
Mhm.
neutrino, anti-neutrino? Because anti-neutrino now is neutrino if it comes out to be Majorana.
Uh-huh.
So what happens? This is
Yeah,
my
so
question.
maybe then we would need just a single plot, not
Mhm,
two plots anymore with these results.
mhm,
So just one single cross section, assuming
mhm.
that the data we are reporting now represent this neutrino Majorana.
Aha,
So yeah, I think this would be the case. But
okay,
yeah, as I mentioned, Professor Elael, I would be very happy to contribute somehow with your effort. Now that this data is
okay,
available, we have some trainings going on, some tutorials going on to
okay,
make this accessible for the public. And if you have any student interested in doing this
okay.
kind of analysis, it would be nice to.
Be sure we will disturb you. Be sure.
Yeah. Yeah.
Look, I'm just to finish. I'm very glad to see how much you progressed. I mean, you were one of my best students that year. You really was a very serious student, always coming to questions, and you made me think about things that I had not thought in my course. So it's very glad that you and Elio, Elio did a very good work with you, and you are at the Fermi Lab, learning much more, developing much more. And so my congratulations for your growing up, for your work, and for your future. I hope I'm sure that you have a lot of potential to be a very, very fine physicist, independent physicist. And I'm very glad also to meet my colleagues here in the committee. I didn't know these people. No, I also was very attentive to what they were saying, because for a theoretician, today for me, it was almost a Chinese, but your thesis was very well written. I could know what I was reading, because sometimes even with theoretical physics thesis, sometimes we feel that we are lost, but your thesis was far from my field, but I was never lost. I was always very located, knowing what you were doing and what you were trying to convey. So my congratulations, and have a very nice future as a physicist. And Brazil, sometimes we'll need you too, maybe. But maybe you can be very useful being also outside Brazil. But if you are coming back, you are most welcome. Thank you for the participation in your thesis, and I now give my word back to our president, Hélio da Mota.
Okay,
Thank you.
thank you
Thank you
very
very
much,
much.
Daniel. So now we go to Professor Giovanni Alves from CBPF for your questions and answers. Okay, thank you. So just want to thank you and you guys for inviting me. It's very nice to see this work done. I hope you can get well. One of the questions is actually that you said that you still have to in the end of your talk you said that you will do some other thing, but didn't you already submit this to publication? I think you mentioned that at least.
Oh.
I don't know. I'm a bit confused here because you mentioned in your thesis publication that's it's going. I mean, it was submitted to. It's in the archive. So
No. Yeah, it's not on archive yet. We're still working on this analysis. And yeah, we're planning to submit this to a publication. We need to resolve these problems we have
So
with
you
this.
only submitted after you do this other.
Yeah, we are planning to
Steps
provide.
yes,
Yeah,
this, investigating interaction with the effect. So
yeah,
okay, you
we're
still have to do this before you submit.
Yeah, that's right. We need to look at this SIS multi-quark region, and with that result, then we're gonna publish all of them in a single publication.
Great. Okay, thanks. One thing that I found, I don't know if this is the rule or not. In the abstract, you quote that this study is based on 416,000 whatever, no, muon neutrinos. But in the paper, you actually quote the protons on target. So which one is the standard? Protons on target, so number of events. I'm a bit confused too, because I mean in the LHC experiments we quote the luminosity because we normalize everything by luminosity. So you're normalizing by what? By protons and target or by that?
Yeah, sometimes we use we put this information about the mean energy at 6 GeV, and sometimes we report the POT. But I think, yeah, the POT, something more precise, you have exactly the number of the protons on target that generate those neutrinos. So yeah, for a future publication, we have to think about that, how to report this information.
Good. Yeah, because I mean, you have to normalize something.
Yeah, right.
Okay, so yeah, one question is that you mentioned that you still have in Minerva some other targets. Is the helium, which is not this guy, in target is hard to get the results from that because that would minimize the nuclear effect. So
Yeah, that also could be the case. We have one analysis on helium. I don't know to what extent that could be difficult to do, but yeah, that's also a nice idea to study this helium to see this final state interaction, the medium effect, the medium nuclear effect. It's also a nice idea.
yeah, I understand that because of the mass, you probably have less events there because the main target you have a lot. I don't know how many tons of mass, and the helium you have just very few. Yeah, 0.25 tons to 8 tons, so it's going to be a very much less events there. So, but maybe it's worth a try. I don't know. Because then you don't have so much problem with nuclear effects or something. That's
Mhm.
okay.
Yeah, sure.
Yeah, one thing is, in your thesis, in your text in the thesis, you just give a brief information on oscillations. And I think in your presentation you did a very nice with slides on that. Maybe you could add that to the thesis, to the you know to the text, because this is the thing of the moment, right? The oscillation is something on the agenda
Yeah,
of
sure.
everybody on the treatment. So maybe
Yeah,
you
sure.
could add some of that to the maybe in introduction or whatever. Just put a little bit more of information on oscillations, that just for people that reads to to have a feeling of what's people that are not in the business of neutrinos. Maybe it's nice to see a good introduction of oscillations.
Yeah, sure. I
But
I
yeah, that would be
admit.
helpful, I think.
Yeah, I admit I had briefly described oscillation phenomenon there in my thesis in introduction in the SIS part, but yeah, I can expand the discussion and give these more details as I provided here on my presentation. Mhm.
Good, good.
Yeah.
So one thing I think in slide 21, and just to move up a bit,
Okay.
you mentioned that those now there are two things here. One, you mentioned that those regions, the side bands do not actually touch the signal region. Did I understand it right? Right?
Yeah, that's right. We have these gaps to prevent signal contamination.
Yeah. Okay, but another thing is that Howard has said that the cis region is actually not defined by W, but by Q square. So does it make any sense to do this thing in W, or I don't know?
Yes, W is the key. By everything like right now.
Daniel,
Yeah, we're losing your speak.
I think I lost your signal for a while.
Oh, can you hear me now?
Now I think we can hear.
Yeah, it's better.
Okay, sorry. So yeah, as was mentioned, the W
Lost again.
was the
Yeah, we're losing
Yeah.
most of your words.
like
Can you repeat it? We couldn't catch it. I think the internet's bad.
He's frozen a little bit, no?
Yeah.
Yeah.
oh,
Well, I can say it's not site-wide.
Connection is not. We lost. Did we lost?
how
I'm trying to call him. Hello? No, nós perdemos. We lost you. Try to reconnect. Somehow it's not working. Try to reconnect it. If are you using Wi-Fi from Fairlab? But something's wrong. Okay, try again, be disconnected and connect again.
At least at my floor, the Wi-Fi at Fermilab is okay.
Huh.
well, maybe it's good that he goes out and he comes back again, or he enters again, just to
Maybe
disconnect.
go out and back again.
Yeah, maybe.
There should be a good connection there for my life.
Yeah, yeah.
And if you disconnect the safety signal, go and connect again.
Elio, while he is doing that, can I comment a little bit about the W issue that was just being discussed?
Sure.
Yeah.
Go ahead.
Yeah, what you said is certainly true with shallow inelastic scattering being defined by Q squared.
I think
W does enter into the fact that we want to, one, choose a region of our search where the resonant production is minimized. So we choose W greater than 1.5 to eliminate the delta contributions. Now, within the W region, we look at two Q squared regions, one Q squared greater than 0, the other Q squared greater than 1. And the Q squared greater than 1, as I've mentioned before, tends to isolate the actual shallow inelastic scattering multi-quark region. And that is the region where non-perturbative QCD is dominant. And we define deep inelastic scattering contemporarily at Q squared greater than 4. So 1 to 4 is roughly the shallow inelastic scattering region in Q squared. W enters, as I said, to remove and reduce resonances. And it also, given Q squared and W, it gives us X. So Q squared limitations and W limitations together give you the X distribution that you can consider. And that in turn gives you the probability of interaction.
Good. Great.
Okay, so that's how Q squared is dominant, but W is important to understand the reduction in the background from resonances and to understand the probability of finding a quark with which to interact.
Okay, I think he's back.
Can you hear me now?
Close to the microphone.
Can you hear me now?
Yeah, sure.
Yes.
Okay. Yeah, sorry, it was my connection. I think Jorge was explaining this W dependency. Okay, sure.
So that's cheating. You just go ahead and get out just to avoid the question. No, no problem. No, that's fine. Okay. I just have one more thing is that looking at the references, this is something that I always find in all the thesis. Try to put the DOI, the document identifier for every single reference if you can find it. Because
Okay.
then it's easy for people to find the reference. So, I
Yeah.
mean, if you have the PDF, you just click it. Okay, but if you have a hard copy, you probably should use the DOI.
Oh, I see. I see.
So that's very great. Thanks for the. So before the presentation, mention something about using artificial intelligence. Oh yeah. So go ahead. Okay. No. I was discussing that with him because I was going to ask you, and he already. But I'm going to ask you anyway. So in the unfolding procedure, you use the good anode, Agostini method that used about 20 years ago. But nowadays, for instance, Atlas is using artificial intelligence for the unfolding. So did you actually try to look at it or something?
No, I didn't try any other unfolding methods, but I know that nowadays it's an emerging technique using machine learning to perform also unfolding. So I know there are some studies going on also in the neutrino field, but I haven't tried any other unfolding procedure.
Yeah, Eddie was telling me that probably people in the collaboration wouldn't accept it. So do you think it's true? I don't know, because of course they have to prove it that it works.
Uh-huh.
Better than, and of course it's better than the other one. Right?
Uh-huh.
So people just say, no, just use the old one that we trust.
Yeah, right. Yeah, I think that's possible if someone is interested and coming now, like in the beginning of the PhD, try to perform some work like that. If it might be worth it to do it, but I think it's not something like people might have some resistance to this, but as we mentioned, if you answer all the questions and try to prove that your method is better than this one we have now. So I think that's possible.
Yeah.
Yeah.
Okay.
Mhm.
Yeah, before I forget, since you mentioned working on the this liquid argon thing, maybe on the appendix you could do a brief introduction to Dune, maybe because just to make the because you mentioned the experiment, but you don't say much about it.
Oh, I see. Okay. Yeah, I can.
That would be nice for
Hmm.
for people that are not in the field, of course. The people that are in the field, they know everything about the training. So
Yeah, I know what you mean. In my appendix regarding this detector LATRPC studies, I think, yeah, I mentioned Dune here, but I think this is kind of work not limited to Dune. This could be this filter we tested could be also applied like in dark matter experiments, but nowadays they are using not liquid argon, they are using xenon that doesn't have this doesn't suffer from this impurity as much as liquid argon, but I try to not be limited to Dune. But I can provide more information on Dune here. Yeah.
yeah,
Mm-hmm.
okay. Yeah, we actually used liquid argon before, but that was for the
Yeah.
color, so we didn't have to prepare.
Yeah.
Anyway, thank you. Thanks again for the and I hope you have a nice postdoc there.
Yeah. Thank you. Thank you so much for being here, for your comments, your questions.
Okay. So now I have to Larissa, are you still there?
Sim.
Ok, I have to change to português. Nós acabamos aqui, você pode abrir a sala reservada. Colocar o pessoal na waiting room. Okay, now Larissa is going to send us to a private room, so we can
É só
discuss.
aceitar na tela de vocês, tá? Vai aparecer na tela de vocês.
Okay, so just accept connecting to the Everyone's back there? Larissa?
Oi?
Ah, estamos de volta, né? Estamos de volta.
Sim, todos de volta.
O YouTube também funciona.
Funcionando normalmente.
Okay. So, we're back. Daniel, the committee has convened. We have discussed your thesis. The general opinion that your work is very good and it has been approved. So we have a
Thank you
new
very much.
offer in the market. And we know that you are not unemployed, as we say here. And the major suggestion is that we should change the title of the thesis
Okay.
because the way it is not really covering the SIS region because of the Q square bigger than zero. So we just gonna make a change in the title. This is not a problem.
Mhm.
And if there are any other comments, people are gonna email you and me. But in general, people have no objection to your work, your presentation. Just this small question about the title.
Okay.
Okay. So congratulations, dude.
Thank you so much. Thank you.
Congratulations.
Congratulations.
We have
Parabéns.
Well done, Daniel.
plan because usually when someone presents a thesis and approved, invites the committee for a beer or for something more. And we have to wait for the opportunities. But I guess that you're gonna be here in Rio, in Brazil, for the Dune collaboration meeting. And maybe many of the other guys from the committee are gonna be here, so this will be the opportunity. So, Daniel, anything to say?
I just thank you, everyone, for being here, the committee for all the comments, questions, and also thank you to you, Elio, my supervisor, for all the support, the generosity, also John Paley, Jorge Mofin, everyone here. Thank you so much. And
In fact, I should say that you are clearly one of the best students we have here at CBPF in the area. That's good because the other students are now watching in the YouTube. They should take this as a model. Okay, they have to do it as well as you did. Right, Gabriele? Gabriele got the answer, but she's watching that. Okay, so again, congratulations, and I hope to see you soon. And keep in touch because we have to time to give. And to the members of the committee, Larissa is going to send a document for you all to sign.
Okay.
And of course, usually the document is in Portuguese. You should know Portuguese by now. But anyway, I send a basic translation. It's basic document confirm the approval. I send a translation that should not be a problem.
Elio, perhaps Larissa has to send the document with the new title of the thesis, no?
Yes, and the title, yeah. Yes, I talked to her.
Just tell her, okay.
Yeah. And she should change this today, send it today, or maybe tomorrow morning.
Okay.
Good question, yes, we do that. So I should thank you all for accepting, taking part of this committee. It's always valuable to have the opinion of different people. We can even have LIL, that's, as I said, a theoretician. But it's good to have people with different views looking at our work. Okay, so thank you all again. It was a pleasure having you, and I hope you can continue doing something in Minerva and the other experience with me. We hope that the line of life can cross again sometime. Okay, thank you.
Bye-bye.
Bye-bye.
Thank you.
Congratulations.
Thanks, everybody. Congratulations again. Bye.
Ciao, Larissa. Ciao.
Larissa,
Tchau, tchau.
agora, tá?
Hasta luego.